Okay, let's talk about functions. So I think functions are a really important stepping stone in the math curriculum. It's kind of when you go from just basic algebra to more advanced algebra and pre-calculus. Also, functions are a really crucial idea in calculus because calculus is all about the analysis of functions and how they change and applications regarding that. So you really need to have a good idea of what a function is before you go into calculus. So in this video we're going to look at what are functions, what is an example, and why are they useful. So first off, what is a function? So functions are rules that map a set of inputs to a set of outputs. So you give the function an input, and by some rule the function is going to give you a corresponding output. So let's look at a picture. This is one of my favorite pictures in all of mathematics. Looks like it's out of Dr. Seuss. But this is your basic function machine. So the function machine takes in an input, does something to that input, and gives off an output. So again, it's going to map all the inputs to certain corresponding outputs. And that's the idea of a function. So a function machine helps conceptualize that in a picture. Let's look at some concrete examples, like a doubler function. So this function takes in an input of a number, and then on the inside the rule is it maps a certain input number to twice that number. So it's going to map 3 to 6, it would map 10 to 20, etc. The point is the input is a number and the output is 2 times that number. That would be an example of a doubler function. Functions don't always have to be numerical, even though most of the time when we're doing math we're talking about mathematical numerical functions, but you could also have something like a translator function. So this would take in a word in English or some language and then translate it into a word in another language. So here we have cat in English and gato in Spanish. So that's Spanish for cat. So this would be a translator function. It takes the input in English, gives the output in Spanish. So that's an example of a non-numerical function, although again most of the time we're talking about mathematical numerical functions. So what do functions look like mathematically? Well, this would be the definition of a function, of a certain function. We have a name. In this case it's f. F is a really commonly used name for a function because f could stand for function. So you see that all the time. Parameter is x. It doesn't have to be x. I'll show you an example in a minute that doesn't use x. But it's kind of arbitrary what the parameter is. And then the definition or rule is usually some operation on the parameter because the parameter is going to be the input, and then the operation tells you how to take that input to an output. So this is the doubler function. So it takes in an input of x and gives an output of 2 times x, where x is just an arbitrary, it's a variable. It stands for whatever the input is. So when you look at f of 3, that would be when x equals 3, so it's going to do 2 times 3, that makes 6, so the output is 6. F of 4 gives 2 times 4 is 8, f of 64 is 128, so you see how the doubler function works mathematically, and you can see how this definition relates to that. Let's look at another example. Here the name is g, so it's g of t equals t plus 4. So again, the parameter is not really important, it's kind of arbitrary what you choose that to be. Often t is used if you're talking about time, but it doesn't have to mean that. It can really mean anything. So g of 3 would be 7 because it would be 3 plus 4 makes 7. G of 4 is 8. G of 64 is 68. You see how that works as a function. Now there's an important note, which is that to qualify as a function, the rule must map every input to exactly one output. So you cannot map an input to more than one output. So here would be an example of a non-function. This is not a function. Say you wanted f of x equals x plus or minus 3. So that doesn't make sense. You can't have 5 map to both 8 and 2. Because as soon as we open that door, are you going to let somebody make a function that maps an input to 10 different values? Then how do you know what each one of those means? A function is supposed to have a specific meaning. So if it's going to give 10 outputs for one input, how do you know what each of those 10 values mean? A better solution would be to make 10 different functions, and then they all have their own specific meaning. So we don't want functions that give more than one output for a single input. It is okay, though, to have a function that gives the same output for more than one input. So just as an aside, if I have f of x equals x squared, this is still a function, because even though f of 2 is the same as f of negative 2, because those both square to 4, that's okay. The point is the function still has a meaning. It still says, I'm going to take your input and square it, so it's okay that two inputs can square to the same output. So why are functions useful? I've listed 3 reasons here: encapsulation, potential for analysis, and the idea of an inverse function. So let's look at encapsulation. What do I mean by that? I mean that functions encapsulate an entire mathematical operation into just a small, succinct package. So say I'm looking at a grocery store list of some sort, and I have the price of apples is $1.50 times the number of apples. So I made a function a of q, which would be like a would stand for apples and q maybe quantity, I don't know. But a of q is $1.50 times q, so that's the function that gives me the cost of buying q apples. And I have another function that gives the price or the cost of buying a certain number of melons, $3.25 times the number of melons. So m of q is 3.25 times q. Now I can really easily say in a succinct way the total cost of buying 3 apples and 2 melons, because it's a of 3 plus m of 2. I can kind of forget about the details of that and look at this on more of a big picture standpoint. So that's one great thing about functions, is how they can encapsulate a whole mathematical operation, so you can look at things on a bigger picture. There's also the potential for analysis, and this is huge because this is what calculus is all about. You're looking at the first part of calculus, looking at how things grow and comparing that. So here's an example of analyzing growth. Say I want to look at a function like f of x equals x squared. I want to look at how much that function grows between 2 and 3, so I'm going to look at f of 3 minus f of 2 and compare that to how much the function grows between 3 and 4. So I look at f of 4 minus f of 3. If I calculate this out, f of 3 minus f of 2 is 9 minus 4, which makes 5. f of 4 minus f of 3 makes 7. So that tells me I can conclude there's more growth between 3 and 4 than there is between 2 and 3. And so this could have a lot of applications. Maybe you're some sort of financial planner and you want to figure out, you know, how much more is my money going to grow during this year versus an earlier year, or some application like that. These sort of bits of analysis have a lot of applications, and that's what calculus is all about. So functions provide a great way to analyze operations. Finally, the idea of an inverse function is undoing a function. It's going the other way. So here I have the function machine diagram. In this case, f of x equals x plus 3. But say I already know the output, and what I want to know is the input. So maybe I know the output is 9, and I want to know the input. Well, there's the idea of an inverse function, which is a function that undoes the original function. So this lets us go from the output back to the input, which in this case would be 6, because f inverse of x in this case is x minus 3, because that would undo f of x. Here's kind of a more complicated picture where we have f of x and f inverse of x in a row here. But remember that all f inverse of x is supposed to do is undo f of x. So if I put 4 into f of x and then put the result of that into f inverse of x, I should get 4 back, because f inverse is going to undo f of x. By the way, f inverse is denoted by this little minus 1. That's how you denote that is an inverse function. So f inverse of f of x, the f inverse and the f sort of cancel, because the f inverse undoes f and just gives you x alone. So to find the inverse, you isolate the parameter in the definition. So take that function earlier, like the cost of a certain number of apples. The price is $1.50 times the number of apples. That's great if I know how many apples I want to buy, but what if I want to go the other way? What if I know how much I want to spend, and I want to know how many apples I should buy? That would be a case where we want the inverse function. So here's an example. Here's the function a of q is $1.50 times q. What we want to do is isolate the parameter in that definition, because we want to know, we want input equals some function of the output, right? We want to isolate the input, in this case q. So we solve for q in terms of a of q, and we just divide both sides by $1.50, and we get the a inverse of p, where p is the price, is p over $1.50. $1.50, and that would tell you the number of apples is the price over $1.50. So that's basic functions and inverse functions. I hope this has helped firm up your understanding of functions. Thanks for watching, and I'll see you in the next video.